Welcome back to this course on computational thermodynamics and kinetics of materials. The intensity of thermodynamics is going to continue for one more class. Today we will cover how classical entropy, the entropy that we saw in classical thermodynamics, is equal to the statistical mechanics entropy. Okay. Then we will see what are the different types of entropy, and then there is a need for new state properties. You see, when we talk about entropy, we talk about systems entropy plus surroundings entropy, right? So that is a problem. So is there some new state properties which can give us some advantage, like let's say only measuring the changes in the system? Okay, so we will try to see whether that is possible to get. In that pursuit, we will see what is enthalpy, Helmholtz energy, and Gibbs energy, and we will see that Gibbs energy has quite a few advantages. And then we will define the what we saw in the second law about feasibility of processes in terms of Gibbs energy change, and what does it ultimately entail. First, let's see how the statistical entropy is equal to the entropy that we saw in classical thermodynamics. In classical thermodynamics, we approached the Joule expansion and figured out the entropy change in that. Now we will see entropy change through statistical mechanics. So this is what we saw in classical thermodynamics. There is a free expansion, a irreversible adiabatic expansion, and volume expands to twice the initial volume. That's what the case of Joule expansion is. And from classical thermodynamics, we have obtained that the entropy change in this process is totally the entropy produced because there is no heat exchange, and delta S came out to be R natural log of 2. From statistical thermodynamics, we'll see that initial entropy S1 from the formula of Boltzmann, K natural log of W1, and once it reaches the final state, we will still use the same formula and figure out what is the entropy in the final state, so that we can calculate the entropy change. So this is the entropy in the final state. Now our job is to figure out what is this W1 and W2. So that is challenging, because you see, when we talked about entropy change with this W, we were telling that, for example, in the coin tossing example of 1000 coins, where we had 500 heads and 500 tails, we figured out that there are 10 power 299 ways of occurring for this particular macro state. So 10 power 299 microstates we counted. Based on the combinatorics, of course, we calculated. The reason is these are discrete entities of heads and tails. These can be counted. So these are countable entities. That's why we could count it. Okay, quite obvious. But the problem here, when we talk about volume change and all, the things that are going to change is pressure, volume, temperature kind of things. So macro state is represented using these state variables. In classical thermodynamics, that is obvious. But how do we approach this in statistical thermodynamics? So we have to these are continuous entities, right? The pressure, volume, and temperature. These are not discrete. These are not countable like head and tail, right? So how to do that discretization for these things? We have to discretize the positions and momenta. Think about positions and momenta, position of particles and momentum of particles. They basically constitute the macroscopic states, the macro states of pressure, volume, and temperature. So these things can be discretized. So in that way, we can talk about microstates for different macroscopic state variables like P, B, and T. When it comes to Joule expansion, internal energy and temperature are constant, we said. Therefore, when we talk about temperature, meaning the kinetic, it's a measure of kinetic energies, right? So we are talking about velocity of atoms. So that velocity is not going to change. Therefore, the momentum is not going to change. What will be changing is the position. Okay. So velocity vis-a-vis momentum of a particle does not change in this case, Joule expansion case. Therefore, positions of particles change. So we are going to discretize the positions and understand the Joule expansion based on discretization of positions. Right. So now volume is discretized into small volumes of size a cube. So this is how we discretize the positions. In terms of discretizing the volume, we are talking about it. So this is initial volume V1. This is the final volume V2, twice the initial one. And now this is discretized into these small volumes, each one a cube. Right. Now each atom can have V1 by a cube positions in the initial volume V1. Think about it. So an atom can sit in any of the small volumes of a cube in the size, right? So in that way, how many positions are there for an atom to sit? These discretized positions are what positions are. We are not talking about, let's say, if this is the origin. From the origin, where is an atom? Is it at a meter distance? 1 meter, 1.01 meter, 1.001 meter? How many zeros? Between 1 and 1.1, there is an infinity, right? So that's why we say this position is continuum. When we discretize the positions like this, we talk about atoms can be here or here. Like say there is some kind of a discretization happening. So in this way, when we discretize the volume, we can talk about there are certain number of positions that are available for an atom to sit, not all the continuous positions. Okay, so in that way, in the initial volume, we have V1 by A cube kind of number of positions for each atom to sit, right? So for capital N number of atoms, we can write W1, meaning the number of ways of occurring in the initial state is V1 by A cube power n. These are the number of atoms. So for each atom, the same possibility is there. So if you put the power n, you are going to get the W1, right? Similarly, for n atoms going into volume 2, the final volume, we can put V2 by A cube. The discretization size is still the same, A cube power n. Okay, now we got W1 and W2. So delta S system is K natural log of W2 by W1. So here we know W2 and W1, we are going to substitute this V1 by A cube power n for W1, V2 by A cube power n for W2. Therefore, we are going to get Nk natural log of 2. This n goes in the front. Now, what is this Nk? We have previously seen that the Boltzmann constant is nothing but gas constant per atom, right? So if this Nk is replaced by R, we are going to get delta S system is equal to R natural log of 2, and from statistical thermodynamics, this is what we get. What we got from classical thermodynamics is also same, delta S system is equal to R natural log of 2. So these two things tell you that the entropy change that we calculate in classical thermodynamics for Joule expansion, we have done a reversible isothermal expansion calculated based on del Q reversible by T delta S. So here we are calculating delta S for Joule expansion directly. We are not converting into a reversible process and trying to think about similar state change and things like that. So that's the power of statistical thermodynamics now. Okay. So in this, we are only talking about W's. Based on that, we can calculate the delta S here. So this is giving us a power to calculate entropy change for any process. Okay, we don't need to do it in a reversible path. Okay, so that's the advantage here. So what you essentially see here is the entropy change that we calculate in classical thermodynamics, where we did not even understand what is this del Q by T and things like that. These are now making sense. So now what we are talking about is the entities, the discretized entities of volume here, and compared to the initial state, now the final state has more discretized, more number of ways of occurring. Therefore, the final state is more feasible, or the final state is achieved from the initial state. The natural process is permitted. So we conclude classical entropy is equal to statistical entropy. Now we can talk about different types of entropy based on this discretization and all. Once we see what is this vibrational entropy, then we will see each of these different types of entropies one by one. So what is vibrational entropy? Let us understand that. Let's think about temperature and energy levels in statistical thermodynamics. If a body is at some temperature it is going to have some thermal energy. We can quantize that energy, meaning discretize that energy and talk about energy being in some kind of a bundles, not a continuum. If we say 5 quanta of energy is there for this particular body, these two curly things here, they represent 1 quanta of energy. It's as if the atom is vibrating in that range. Okay, so that is 1 quanta of energy for an atom. 5 quanta, let us put 2 more quantas to this second atom, 1 quanta to each of these atoms in the bottom. Therefore, the total is 5 quanta. Okay, so the 5 quanta of energy is now distributed to 4 atoms like this in this case. If we think about hot and cold bodies joining and becoming warm, we can check based on statistical thermodynamics whether that process is permitted or not. Let us think about this energy quantized and distributed to these particles here, atoms here, in hot and cold case. In hot case, there are 5 quanta of energy. In cold case, there is only 1 quanta of energy. This 1 quantum of energy, how can it be distributed into 4 different atoms? In 4 different ways like this. The first atom can have that 1 quantum of energy, or the second atom, or the third atom, or the fourth atom. In this way, there are 4 different ways of distributing this 1 quantum of energy to 4 atoms, right? So this is the number of microstates here. What about the hot body? 5 quanta of energy. How many ways of distributing it to 4 atoms? The number actually is very high. We cannot put it pictorially here. We have to use something called stars and bars problem in combinatorics, which is having this kind of a formula. If you apply this, what you will get is 4 number of atoms and 5 quanta of energy. If you substitute this as n and k, you will be getting 56 number of ways of arranging these 5 quanta of energies between 4 atoms. So this is a big number now. Now what happens if we join hot and cold? Let's say we are joining them within an adiabatic container. Let's treat one part as system, one part as surrounding. Hot part is system, cold part is surrounding. You can choose the other way around also. What we are ultimately going to check is if this is the system and this is the surrounding, and it is kind of closed now within adiabatic container. There is no mass coming in, there is no heat coming in also, let's say. In that way, this is the entire universe now. Okay, we can check whether the entropy increases for this system plus surrounding. Okay, let's see that. The natural process that we are expecting to happen intuitively is that hot and cold becoming warm. Okay, the initial entropy of this part is 56 and this part is 4. Not initial entropy, the initial W for these two cases. And once it becomes warm, this is a very crude way of atoms as if they are getting warmer like this, but you get the point. Okay, so here the final state is 3 quanta of energy distributed to 4 atoms here, again 3 quanta of energy distributed to 4 atoms here. So the initial 5 plus 1, now the total 6 quantas are now distributed as 3 and 3 in both the sides, and WF, the final W values in both the sides is same, 20 20. Right. Now if we take the Boltzmann's equation and calculate the entropy change, the final entropy, the K natural log of final entropy minus K natural log of initial entropy. Okay, so since it is in the natural log, we can put them in division form like this: K natural log of WF minus WI. We will get, if you substitute 20 by 56 here, we are going to get the hot side, the entropy change minus 1 Boltzmann constant, which is less than 0. All right. For the cold side, we are going to get entropy increment 1.7 K, 1.7 Boltzmann constant, which is more than 0. Now, delta S total system plus surrounding is minus 1 plus 1.7 is 0.7 K, which is a positive number. Okay, now the total delta S total has become positive, right? So this is what we need for a natural process to occur. A process is feasible if the total entropy change is positive. That's what we told from second law of thermodynamics. Now in this case, it is a positive number, 0.7 K. So therefore, the process is feasible. Hot and cold bodies becoming warm is feasible. things that we have calculated just now are called vibrational entropy because it is talking about thermal energy being quantized. So if we see what we have done over the last two classes is like countable entities are connected to entropy. For the very first example that we started to understand what is microstate and macrostate is numbers in dice, okay, countable. Then heads and tails in coins, countable. Tiny units of volume, the A cube that we saw in Joule expansion, that is countable. Quantized thermal energy level, 5 quanta of energy to 4 atoms we said. So there we have quantized the thermal energy. These are again countable. Okay, like that we can talk about several entities. So I'm using a very generic word entity. I'm not even telling what is it. Okay, so anywhere you see quantized or discretized entities to count in a system, we can talk about entropy there. Okay, we can calculate a W there. This is quite powerful. So when there are countable entities, entropy arises. From statistical thermodynamics, we can calculate it. Right? Entropy types we are going to see based on what are these countable or discretized entities. Entropy arises wherever different ways of arrangement of any countable or discretized entities are present in a system. For example, in Joule expansion we saw entropy is due to positional configurations of atoms in space. Right? Now what is discretized entity here? Positions in space. Okay. In metallic glasses, this entropy that is calculated due to positions is referred as configurational entropy. Of course, the word configuration is a very generic word, okay, and this is not a unique name for this particular kind of entropy we are talking about. A better name is positional configurational entropy. Okay, so there are configurations in positions, therefore this is called positional configurational entropy. Okay, you will see that the same name comes once again for a different entropy as well, configurational entropy word. We will again give a different name to that also. Wait for a couple of slides for that. Now this is a hot body with some quantum of energy. Atoms are basically vibrating. We are basically putting vibrational energy states in a quantized manner. Therefore, in a solid at finite temperature, anything above 0 Kelvin is finite temperature. Entropy is due to configurations of vibrational energy states among atoms, right? So these vibrational energy states are the countable entities now. So in this case, we call it vibrational entropy, and this is applicable for any temperature above the absolute zero for all materials. Okay, vibrational entropy. And then there is electronic entropy, which is due to configurations of excited electronic energy levels. So they can also be discretized. And then there can be magnetic entropy, which is due to configurations of magnetic moments. Right. So this particular thing, vibrational entropy that we talked about, this is in solids. What about the gases? In gases we have translation and we also have rotation. And these things in a gas at a finite temperature, an entropy is due to configurations of translational and rotational energy levels as well. Therefore, we have to find a different word than vibrational entropy. This is a better word, thermal entropy. Okay, it includes many contributions. All entropy contributions that are temperature dependent, like vibrational, electronic, magnetic, this translational, rotational, all these things can go into this term, thermal entropy. So this is a more useful term, like the entropy that can be measured by changing the temperatures. Okay, that is thermal entropy. So in solids, thermal entropy includes vibrational, electronic and magnetic entropies which depend on temperature. This is a quite important type of entropy. In solids, an entropy arises due to configurations of different chemical species in lattice sites. Okay, we will see about it in detail in future. This particular type of entropy is referred to as configurational entropy. Again, the word configurational entropy comes, which is not unique. In this case, we are talking about different chemical species mixing in lattice sites, right? Therefore, a better name is chemical configurational entropy. Okay, Chemical species you can imagine as elements. Okay? Red atom and blue atom are two different types of chemical elements. They can arrange in different number of ways, constituting one single macrostate. Okay, therefore we can call this entropy as chemical configurational entropy. Now that we have covered the different types of entropies, we will now see a problem with this entropy. Okay, we need new state properties. Entropy is not good enough. Let's see that. So what is the problem with entropy? We know entropy change can answer about feasibility of phase transformations, reactions, etc. Any process feasibility can be checked by entropy change. But problem is we have to find out entropy change for system and surrounding. That's a big problem. System at least is in our control, surrounding is not. Okay, so that's a problem for us. So finding out microstates of various entities in system and surrounding is in general an extremely difficult thing to do. Okay, so it's extremely difficult to measure, control and estimate. Is there any state property of only the system? Okay, it's a system state property that can answer the question of feasibility of a process. If we have such a state property, it will be quite useful. Okay, and also, is there a state property which is easy to measure, control and estimate? Although it is only for the system, is it easy to measure and control? That another characteristic that we are looking for a property, state property. Let's see that. How about internal energy? Is it such a property? What do we know? Let us collect our information from the first law and second law and see whether we can get any help in this regard. Okay, first law is giving us du is called del q minus del w, and del w is the work done pdv, right? And second law gives us ds equal to del q by t, and of course this del q is del q reversible. We can write del q is equal to tds from this. Combine first and second law. If we combine these two, we can write for which is true only for reversible processes, du equals tds minus pdv. So in place of del q, we are writing tds. In case of del w, we are writing pdv. So from second law, we are putting this term. Therefore, this is the combined first and second law. Here we are talking about changing the state property u. Can this change tell us anything about whether a process is feasible or not? Answer is no, because it still has ds. This ds is something for system and surrounding, right? It's not very useful expression now. Entropies of system plus surrounding are still needed to use this. Moreover, the natural variables of u are s and v. See, ds, if ds happens or dv happens, only then du can happen, right? The changes in s and v can bring about changes in u. So these two are problematic now, because v sort of a change in volume can be sort of tracked, but change in entropy, as we said, cannot be tracked that easily. Therefore, it's a problem. So u being function of s and v, these are the natural variables of u, and these are not easy to experimentally control, okay, especially the s part. Now let's see whether any other property can help us. So we are going to see these state properties: Helmholtz energy, enthalpy and Gibbs energy. So how to have easily controllable variables, that's what we are going to search first. Du is equal to tds minus pdv, we said, and this first part we will take, where u is function of s. Let's take u in y-axis and s in x-axis and see how the function is. U as a function of s looks like this. Now in this, if we take some point here, u is this much and correspondingly the s is this much. In this case, at this point, if we draw a tangent like this tangent has a slope of t, right? So this part is looking like y is equal to mx kind of thing. So this t is equal to du divided by ds. So this height is du, this part is ds. Now the same thing can be drawn like this. So this entire height is going to be u, whatever u we saw, that is this entire height, and this part is going to be s. So therefore this entire height we can write it as ts, meaning this is u, therefore you can keep u here and take the s to the other side, the ts will come, right? So that is this entire length. So if that is ts, then we can write this point as u minus ts. You know, this value is u, right? So from u, you are subtracting this entire height, this height, which is ts. Therefore, this point here in y-axis can be labeled as u minus ts. Now, if we change from this blue point to some other blue point here, we are going to get a different u minus ts, which is this point. Okay, for this point, there is a corresponding u, and from that u, if you subtract this height, you are going to get u minus ts, which is this point. So if we change to some other point, this is going to be the u minus ts now. Why are we doing this? We are doing this because this curve we said is a function of u, is basically u as a function of s, right? And we said it is difficult. S is difficult to experimentally control and measure. So therefore, we are now seeing something else, u minus ts, which is basically tracked from this particular curve. Okay, you see different tangents like this, all of them are governed by this curve. If this curve is not like that, these tangents will not be like this, and since these tangents are like this, they are meeting at different points like this. So each of this point is telling something about this curve here. So therefore, instead of this function, we can use this u minus ts function. Okay, this u minus ts, we are going to call it as a function a. You see u, t, s, all are state properties, right? So a combination of state properties is going to be another change state property, and that we are going to call it as a, and that is Helmholtz energy, a new name to that. Okay, but you see how mathematically it comes. Okay, u minus ts is obviously nothing but u as a function of s written in a different form, right? If we do a differentiation of this, we will see dA equals du minus dTs. Okay, this du we know from combined first and second law, we can write it as TdS minus PdV, and this dTs can be expanded using a UV formula of differentiation, which is minus TdS minus SdT. In this case, you can see TdS positive here, TdS negative here. Those two terms will go. Then we will get dA equals minus PdV minus SdT. This PdV minus SdT is minus PdV minus SdT is useful because we are seeing dV and dt, okay, volume and temperature. These are the variables for A, right? So natural variables of Helmholtz energy are V and T, and these are easy to control. Okay, and where we have started this, du equals TdS, right? And mathematically it has come down to this form. So if we want to do anything like this for any other kind of functions, we can simply take this t and s. So what we are doing here is simply taking this t and s and subtract it from u. That's what you have done here, right? So this t and s is subtracted from this side function u. This is giving us a new state property, right? So this particular process is called Legendre transformation. Okay, and through that we got Helmholtz energy now. So this Legendre transformation can be purely mathematically done. I showed you a graphical way of understanding this. Okay, if I have just started with the Legendre transformation mathematics, this thing might not be that obvious. Now you get the point. This Ts is now going here. U minus Ts is the Legendre transformation. So if we do that, we get a new state property. And this state property has variables that are easy to experimentally control. Now why only du and u and s? Why not we take this part? Okay, u as a function of v. Why don't we take this part? If we want to take this, we can simply take this minus pv, put it like this, subtract it from u. So minus pv is subtracted from u. We will get u plus pv now, right? This is called as enthalpy, another state property. So again we are doing Legendre transformation to get a new state property, enthalpy. If you apply the differentiation to this and use the combined first law and UV formula here, you will see that these two terms cancel out and you get TdS plus VdP. In this case, natural variables are S and P. Again, S is coming as a natural variable, which is problematic, but you will see that enthalpy has a different meaning, very intuitive meaning, and quite useful as we go along. So we'll keep this expression. This is quite useful in the upcoming slides. Now, if we are going to get the most important function, Gibbs energy from Legendre transformation. For this, we are going to take both the terms in the right hand side together and do the Legendre transformation. So U minus TS minus of PV, everything together in one go. So therefore, if we combine this U minus PV as U plus PV, then we can write it as H, right? So H minus TS, which is Gibbs energy now. So if you take this and do the differentiation, you will see that for dH you have to substitute what we got in the previous slide and apply it here. You will see that dG equals VdP minus SdT, right? Instead of this, if you start you started with U plus PV as H. Instead, if you start U minus TS as A and keep this plus PV as just like that, then if you apply the differentiation, you will see that this is also coming down to this particular formula again, VdP minus SdT. So what we are seeing is natural variables of Gibbs energy as pressure and temperature. Okay, quite useful and easy to experimentally control these variables. Right. So we got these different functions. Internal energy U as du equals TdS minus PdV from the combined first and second law. This is where we are starting the Legendre transformation, and when we do Legendre transformation in different ways, we get these three different functions H, A and G. Their natural variables are here. So H is function of entropy and pressure, Helmholtz energy is function of volume and temperature, Gibbs energy is function of pressure and temperature. Okay. So there is no need to be confused here by seeing these many functions. These are all coming from the combined first and second law. Okay. These are quite simple only. Right. About this Gibbs energy, we are going to see more because that is going to give us a lot of advantages. The first advantage we will understand from this. So to understand the first advantage, we have to look at this formula. We have done that dG equals dH minus TdS minus SdT. At constant temperature, we can simplify it as dH minus TdS, or in a finite form delta G equals delta H minus T delta S. Okay. This formula is quite important. We will be frequently using this. Now, what is the advantage we are talking about? From second law, we say ds system plus ds surrounding must be greater than or equal to 0, right? Assuming ds surrounding happens reversibly. You know, surrounding is a huge reservoir, so entropy change in that happens reversibly, let's say. Then we can write from the combined laws, adjusting, keeping only ds on one side, we will put the temperature below these other two terms, du by T plus PdV by T. Okay, this is coming from combined laws. We can write ds system plus, instead of ds surrounding, we will write du surrounding by T plus PdV surrounding by T, right? As combined laws we have written for only reversible cases, right? Therefore, this part only we can replace, ds surrounding only we can replace using the combined law. ds system we don't know. This can be, if this is a process happening reversibly, we can happily use this combined law here also, but we don't know whether it is a reversible or irreversible process in the system. So for that generic case, we are doing this. For the surrounding, we can take it as the reversible case. For the system, we are not touching anything. ds system we are going to keep. Therefore, we will keep this symbol also. For if it is a irreversible process, the entropy change of system plus surrounding will be greater than 0. We will keep that here. This equal symbol is only for the doubt that whether this side is also reversible. Okay, so let us keep it like that and proceed. ds system minus du system by t minus pdv system by t. Now what we have done is, since du surrounding and pdv surrounding is nothing but what is happening in the system in the reverse way, du system negative and pdv system negative. You know, del q reversible is basically the entropy transferred, right, from system to surrounding. In that case we can write it as negative of these two terms, but we will replace the subscript from surrounding to system, right. Then we will do this t here and multiply the entire thing by -1, let's say. Then we can reverse this symbol to this less than or equal to 0 minus TDS my system plus DU system plus PDV system. Everything is now system, you see. Then we can write these two things combined and make it DH. DH system minus TDS system is less than 0, which is nothing but DG system being less than 0. This is a quite important conclusion. So we started with this, you see, DS system plus DS surrounding is greater than or equal to 0. That is the second law. So now we have systems entropy and surroundings entropy change. Systems entropy change and surrounding entropy change is what we said is difficult to track. Now we got DG system should be less than or equal to 0. The only assumption we have done in this is whatever entropy change that is happening in the surrounding happens reversibly. If that is usually the case, because surrounding is to be a huge reservoir, so therefore we can consider this to be a fair assumption. In that case, DG system being less than or equal to 0 is enough to identify whether a process is feasible or not. Okay, so this is going to be done only for the system. So to check the feasibility, what we have done is track entropy change of both the system and surrounding. But now what we are going to do is track Gibbs energy change only for the system. Let's see the same thing in a slightly different way. In a natural process, ds total is greater than 0. Only in natural process we are writing. So ds system is greater than del q irreversible by t. But since the surrounding is a huge reservoir or sink, it will undergo a reversible change. Therefore, this minus del q irreversible by t, we can write it to be equal to entropy change in the surrounding. Okay, because this thing is given to the surrounding in a reversible manner. So therefore, this side we can write, take this del q irreversible by t to that side, minus del q irreversible by t, and at constant pressure, we can write ds system minus dh system divided by t. So this DH system we can write in place of del q irreversible at constant pressure. Why? You can see what we have derived for DH in couple of slides ago. We have done that. You will see that at constant pressure there will be one more term there in this equation. That term will vanish, and we will see that del q irreversible can be written as DH system. Then if we rearrange this t ds will, if we write this multiply the entire thing with t ds system minus dh system is greater than or equal to 0. Then dh system minus tds system is less than or equal to 0, right, if we reverse the symbols here. So this is nothing but Gibbs energy change of the system, which is less than 0. So here also we have started from here and we have ended up here. How this has happened is through this part. If you see, dh system by t is written. This is where everything becomes system, right? And this is written in place of del q irreversible by t. Why? Because we considered this part, surrounding, whatever happens in the surrounding, that is happening reversibly. This is what gives us the reason to use this here. Because this comes from the combined laws, right? So this has to be coming through a reversible process, which is here. Okay, that is why you replaced with the replace this del q irreversible by t with the dh system by t. Okay, so in a way, what happens in the surrounding, the entropy change in the surrounding is there in this del q irreversible, and that is elegantly put into this equation as a term that is happening in the system. So that is how we get this particular change, where we end up with tracking only changes in system and talking about feasibility of a change. So this del Q irreversible by T is now minus dH system by T. Yeah, enthalpy change in the system is the heat exchange. So enthalpy is quite sensible, right? Entropy also, Gibbs energy also has these two different terms. Enthalpy and entropy change are there together to understand what is G. So making a physical sense for what is G is tough. Whereas dH is easy. Enthalpy is nothing but heat exchange at constant pressure. Okay, so that way enthalpy is very easy to sense. So now based on this dg, if we write the second law, for an irreversible process del g system is less than 0. For a reversible process it will be equal to 0. For any process we can write del g system is less than or equal to 0. So this is the biggest advantage of Gibbs energy. The second advantage of Gibbs energy is something that we have already seen. The natural variables of Gibbs energy are P and T, which are easy to measure and control, so that we can track what happens in the system. So what are the implications of this delta G being less than 0? This is a very beautiful idea that we are going to discuss now. You see, for an irreversible process, we are writing del G less than 0, delta H minus T delta S less than 0. So now we can take this delta H and T delta S and see what can be the different values for this and how that can satisfy this particular condition. Okay. So delta H and T delta S are going to compete with each other. The first type is delta S is greater than 0, let's say. If delta S is greater than 0, then minus T delta S will be negative, right? If minus T delta S is negative and if delta H is less than or equal to 0, then there is no problem. See, this point, this part is 0 or negative. In that case, the entire thing is going to be negative only. This is anyway negative we are saying, right? If delta H is positive, if the enthalpy change in the system is positive, then if this has to be maintained, what should happen? Delta H magnitude should be less than the magnitude of T delta S, isn't it? This is necessary. Otherwise, this will not be satisfied. Okay, delta H is positive and T delta S is negative. In the competition, we have to get a total negative number. Therefore, this T delta S should be in magnitude higher than delta H. Only then we can get this negative. Right. The other type is when delta S itself is negative. Entropy change is negative now for the system. Right. Minus T delta S is going to be greater than 0. If minus T delta S is positive, this part is positive, then if the total thing has to be negative, how the delta H should be? If delta H should be less than 0, if it is less than 0 and it is magnitude wise it is higher than T delta S, only then it can dominate and make the entire thing negative. It can dominate the minus T delta S part and make the entire thing negative. Okay, so this is a necessary condition now to make the entire things negative. If delta H is positive, we are saying minus T delta S is positive. If delta H is also positive, then there is this particular thing cannot hold. Okay, the process is impossible. Delta H minus T delta S is actually a positive quantity if this happens. Okay, so carefully stop and see what are the 4 different things we are talking about. You will understand there is some kind of a dance between these two guys. Okay. So if when we say delta S is 0 less than 0, it means we are talking about negative entropy change. Okay. So that means delta S according to this Boltzmann formula Wf by Wi natural log is less than 0. Okay. That means Wf is less than Wi. The final state has less number of microstates compared to the initial state. Okay. So this can be possible in nature in the system, but delta H in that case should be negative. And the process we call that as exothermic process. You see delta H we said is the heat exchange, right? If that is negative, it means heat is going out. We call it exothermic process in such a way that it dominates the minus T delta S term and making the entire Gibbs energy change negative. Okay, so therefore this should hold. So in such a way that it increases the entropy of the surrounding more than the decrease of entropy of the system. You see here entropy of the system is decreasing from initial to final. Okay, W decrement is not something that we thought will happen in nature. But if that happens in the system, in the surrounding, the change should be the opposite, meaning the surroundings W should be increasing. It should increase to such an extent that it should overcome the W decrement in the system. Okay, so that is possible. Actually, living beings are actually reducing the W. You see, the DNA in our body is a highly ordered molecule. Amino acids, our proteins in our body are highly ordered molecules. So ordered in the sense that they are not having high W. High W comes when things are randomly mixing, right? High randomness means high W. Okay. In this case, in the body, the biological molecules are highly ordered long polymeric chains. Okay. So how can these random atoms become so ordered? If they become ordered, it means W is decreasing. The carbon, hydrogen, oxygen, nitrogen in our body, they are all highly ordered now. They can be a random heap of these atoms, right? That way W will be really high. Compared to that, when they become an ordered molecule, they actually are becoming more, or they are actually becoming less in the W. Okay, so if W decrement happens in this, then in the same process when that molecule forms, there should be heat going out of the system, and that it should increase the W of the surrounding, the vibration of atoms in the surrounding. That is going to increase the translational energy levels of the gas atoms in the atmosphere. That is going to increase. So if you see carefully what happens in any place, any system where W decreases, it will result in W increment in the surrounding to a larger extent, so that the total W change will be a W increase, not W decrease. So this is a kind of a balance or dance between enthalpy and entropy. This is the basis for the thermodynamic understanding of all the processes in the universe. It's quite profound. Thank you. I hope the lecture is useful. See you in the next video.